All right, so now we're going to tackle this question where we have a baby doing push-ups and we're asked to consider whether the work done by the normal force of the floor on the baby is greater than 0, less than 0, or equal to 0. Said another way, is the floor transferring energy to the baby, taking energy out of the baby, or not transferring energy to or from the baby? That's basically what work means. So I've gone ahead and drawn a representative normal force vector from the floor on the baby's hands, and also just labeled that positive y-axis is pointing up. My answer doesn't change, it turns out, if I pick positive y pointing down. I just picked one just to help us with the math. So we're going to do this problem using the definition of work. So the definition of work due to a force is that it's a line integral of that force dotted into arbitrarily small displacement vector, ds, from S initial vector to S final vector. And we're going to talk about what that S initial vector and S final vector mean in the context of this question. Remember that that's called the force displacement. So first, this is an example of a line integral. So we first need to be able to do this dot product of the normal force with the ds vector. The ds vector has an x and a y component, but the normal force vector only has a y component. So when we do this dot product, the only thing that's going to survive is the normal force times dy, which is the y component of our dx vector. So if that didn't make sense to you, I recommend going back to the 4-1 discussion slides where we talked about the dot product and then also the dot product in a line integral, just to get refamiliarized with that. And notice that the other thing that changed is instead of going from an initial position vector to a final position vector, now our integral is only over the y component of that vector. Y initial and y final are now our lower and upper bounds of our integrals, of our integral. So what does that mean? Well, that initial and final position don't refer to the motion of, say, the center of mass of the baby, which is probably somewhere over here, but instead it refers to the motion of the point where the force is applied. And in this case, the baby is not moving the floor and the floor is not moving the baby. So this, this point right here is fixed. So when we take the integral from, say, y equals 0 to y equals 0, we're going to get 0, no matter how big this normal force is. What that means is that if there's no movement here, there's no transfer of energy from the floor to the baby. So the correct answer here is C, that the normal force is doing no work on the baby. Let's try wrapping our heads around how work works, no pun intended there, with a new example. So here we're going to have a block that's sliding on a low friction surface. What we mean there is that friction is negligible, so we don't have to worry about it. It's going to pass a point x naught, and then some force that we don't know what it's to. We've just labeled it A, but we don't know what this force is due to. It could be a spring, it could be a person, who knows. Some force is going to slow it down, eventually bring it to rest, and then have it reverse directions until it passes that same point again. So this block is undergoing a closed path from x naught, away from x naught, back to x naught. And we're told that when the object gets back to that point, it's moving with a speed v final that is less than v initial. So I'm going to put up here a question for you all to think about. And again, take some time to write down what you think the answer is and why. I'll give you a hint that this one it's hard to do directly from the definition of work. So instead, we're actually going to use the work-energy theorem, the fact that work total equals the change in energy of the system, to try and figure out both the sign of work here and whether it's conservative or non-conservative. So take a minute before you start the next video.